So we have neural nets in here somewhere. And interestingly, they're used in kind of both aspects of it. In the AI class that's coming up next semester, I'm not going to focus on neural nets. It's a lot of, it's mostly brute forcing the decision-making side of things. So a lot of minimax, a lot of searching through all possible futures, find the future you like the best, and then make that choice, that type of decision-making. I do have one assignment that uses genetic algorithm to evolve a neural net. So a genetic algorithm is an optimization technique which can substitute for backpropagation or gradient descent. And then we talk a lot about Bayesian methods or bowel movements, whatever BM means to you. And that wasn't funny at all. Stupid joke. Whoosh. Okay, and what else do we do? And it's a bit more fun. We play games like we write a capture the flag agent that everybody's going to battle against each other in that class. So there you go on there. Meanwhile, on this class, so far we've talked, actually I should shouldn't delete anything. So far we've pretty much done the class like that. And that's pretty much all we've talked about. And there are some other things that I should mention. Well, here's the biggest one, is that neural networks, while we've started covering supervised learning, neural networks are one method used for supervised learning, but there are also several others. And I think I've mentioned before that decision trees are common, random forests, a whole bunch of decision trees. Naive Bayes is one technique that's very popular. And k-nearest neighbor models are also very common supervised learning techniques. And if I have time, I'd like to talk a little bit about all of them. In fact, I do have a little bit of time. Let me talk a little about all of it. Here's a silly little app I wrote. See that picture in the top left corner, that little icon? It's a very famous picture. I'm going to take that little icon and blow it up really big. Now, of course, the original one was done in oil paintings, and it is really big, and you could get high resolution. But this icon doesn't have great resolution. In fact, I could screenshot it. I will, if I can find my mouse again. There we go. Let's screenshot it. Copy to my clipboard. I'll put it in Paint. Paste it there. And just to show you how bad the resolution is, if we scale it up really big, that's what it looks like. Right? Okay. And then does bicubic interpolation and is kind of blurry. So if I take that image, that's all the data I have, and well, that's going to be the same thing as if I do one NN here. What I have done is I have taken this bigger image that I have over here on the right, and it looks like I have great big pixels, but in fact, what I've done is I've treated every single pixel as, these are subpixel locations, and I've found the nearest neighbor in the original sample. That didn't come out very clearly. Imagine the small image, stretch scaled such that the width is the same as this big image, and then all the pixels in that are sample points on this larger image. And now I'm going to interpolate to figure out what are the values in all the pixels between the pixels. So I'm doing super resolution here. If I use a one nearest neighbor KNN based algorithm, basically that amounts to, for every point I'm going to find the nearest point that has a label. And that's going to be the label for all these pixels inside. And as you can see, it just makes big boxy pixels. And that's kind of what you'd expect, right? Yet, it's actually pretty clear that that's the girl's face, isn't it? So, how do you feel about one nearest neighbor learning algorithms? Okay, well, just for the sake of contrast, let's go down here to do a neural network. So I'm going to click on a neural network. This, I think, is a 6-layer neural net, and it's learning, and you can see what's happening is it's starting to fit to the data. And if I actually were to slow it down and take samples at more frequent intervals and then speed it up by playing it on high speed, you could see a really smooth, you could see it smoothly fit into the data points, and it's kind of cool to watch that happen. But even still, you can almost visualize this thing rolling downhill, can't you? And to some extent, you can sort of see it rolling up the sides and back down as it swoops back and forth as it's descending the gradient and finding its way down into some local optimum. And it's not too bad. If I let it run for a really long time, this will eventually get reasonably sharp, but it'll never get really, really clear. Why do you suppose that is? Yeah, basically, there's a very limited number of weights in this whole model. There's a lot of pixels in the image, and if you use a limited number of weights, then it's going to be blurry, just by virtue of that's what it does. So what makes better predictions? The neural net, or say the 1nn model? Now, when you look at that, it kind of looks better, doesn't it? In some ways, although that's sort of what we humans are used to looking at. Here's what we're getting out of the 1nn model, though. The size of the 1nn model is exactly the size of the training data. Every single pixel is part of the model. The size of the neural net model, well, it depends on how many hidden units we have. Now I had, let's actually see how many I had. Okay, let's get out my calculator. I had 2 to 16, so 2 times 16 plus 16 to 16, that's going to be times 16, plus 16 to 16, plus 16 to 16, plus 16 times 3. What's that going to work out to? 848 total values. And remember, these 848 values, if I did the math right, it's close to that either way. These are accounting for all 3 color channels, right? So it's predicting red, green, and blue. Now, if we think about the nearest neighbor one, selection and resize, what's that? It's a 50 by 50 pixel image. So I had 50 times 50 times 3. There are 7,500 values in the model for the KNN version. So in many ways, this is the most unfair comparison I could make, because the KNN model had an order of magnitude more numbers to work with, and so of course it makes a better looking model. On the other hand, let's look at compare some of the properties. Look how fast KNN is. You know, I click on it and it makes all the predictions. It's kind of fast, right? Why is it fast? Well, one is I actually optimized it with a KD tree. Naive implementations of KNN would be much slower. Something else to consider, though. What you were actually watching with the neural network was it was making predictions over and over and over and over because I kept repainting the screen. But you were actually watching the training time, and the KNN you were watching the evaluation time. How long does it take KNN to train? Just instantaneous, right? You give it the training data and it says, thanks, that's my model. That's what KNN is, right? It just stores your training data. It's basically, how long does it take to make a pointer and set it equal to the data they passed you? Almost instantaneous for training. Neural network, when you train, it's pretty much the slowest model available. Anything slower than a neural network, nobody's going to even care, because why, right? So why is it okay that neural networks are so darn slow? Yeah, processes are pretty fast. But the other thing is, they're not slow at runtime. They're slow at training time. So this is training time, and yeah, it's slow. But in fact, every time you see a new image appear, it's run through and made a neural network prediction for every single pixel, and it's doing it over and over and over. They're way faster than the KNN model, and interestingly, the blurriness that you see actually tends to lead to better predictions. Sometimes visual appeal isn't predictive of how well it's going to do. And depending on the random seed, I get different results every time. It's done some weird facial thing here this time. Anyway,
Do you have codes here?
I don't have a convnet here. I really should, but I haven't bothered to code it up yet. Okay, here's 2nn. What's 2nn? Basically, I find the two nearest neighbors and I average, or I take the average of their predictions. You see how it's basically diagonal pixels instead of vertical line squares. It's kind of what you'd expect because we're taking the two nearest ones, which will always be two diagonal corners relative to where the pixel is. If I do 2nn with linear weighting, meaning the closer I am to one pixel, the stronger a vote it has, then it kind of simplifies it even more. 4nn with equal weighting. Now it's made out of a bunch of circles, circle-y like things. 4nn linear weighting, it's kind of looking kind of sharp. 8nn with linear weighting. But now it just kind of looks like it's a blurry original, doesn't it? Okay. Let's look at how great naive Bayes is. First of all, it's darn slow. Second of all, it's doing a bunch of statistics in order to calculate the probabilities of every pixel. And basically, doesn't naive Bayes just disappoint you as a piece of garbage learning model? What the heck, right? Okay, here's why naive Bayes even exists. One, statisticians hate it, but it's kind of statistics based. The idea of naive Bayes is it's very, very incremental. So like a neural network, you can present patterns to it one at a time and it makes it a little better. And then another pattern makes it a little better. But to make it a little better, the math is really easy to do. You just update some statistics. So it's perfect for something like a spam filter. If you have a spam filter, you gather some statistics, you update the model, and it's ready to go again. And by perfect, I mean a neural net would still do better in modern times. But the reason naive Bayes is used is if you throw high-dimensional data at it and you give it enough perspectives, it's actually going to not make terrible predictions. As you can see in 2 dimensions, it does very terribly. So this particular demonstration doesn't show what it's capable of. But it's blazing fast when you're in high-dimensional space. So long story short, it's good for nothing but spam filters. Never use naive Bayes. Okay, let's do a decision tree that makes random divisions. Isn't that interesting? This is, oops. This is basically random forest, except I'm chopping the data in half and chopping it randomly until I end up with a bunch of boxes. Now, and again, don't think of this interpolation demo as representative of the capabilities of the model, but it's giving you some way to kind of visualize how they work and understand that there are other learning models out there. Why are the boxes not, why are they skewampus and misaligned like that? Because I divided randomly. And yet, why does the picture look so darn good? Well, in this case, it's because I had samples at regular intervals all over the entire thing. In a lot of learning problems, that's not how it is. You get a cluster of samples in a high likelihood region and very few samples in other regions. So you'd end up with very big boxes and then very small boxes where you have highly sampled training data. But you can see that decision trees kind of do a decent job of chopping up the space, right? Here's an oblique decision tree. This is a decision tree that doesn't necessarily make axis-aligned divisions. And that's kind of funny how it looks like shattered glass, right? But here's something interesting. If we take 30 different decision trees and then we average them all together, check that out. Isn't that pretty nice? This is an algorithm called random forest. Basically, we've got a forest of a bunch of different trees, and we make those random divisions. But then because they're all making different random divisions, when we average them together, it tends to end up dividing where it should on average, if that makes any sense. So ensembles of decision trees are surprisingly powerful for, well, they're good for this problem and a lot of problems. They don't keep up with deep neural networks on really challenging image recognition problems, but for most simple data mining tasks, random forest is a really great model. I think I've said that before. Here's my favorite one, though. This is an ensemble of oblique decision trees. So it's an ensemble, but they're not necessarily axis-aligned divisions. And this is an ensemble of 30 oblique decision trees. And isn't that a pretty nice blow-up of it? Now, to be clear, these algorithms are not designed for the problem of interpolation. There are image processing techniques that can do super resolution better than these. The purpose of this demo is just to give you an idea of, hey, there's other learning algorithms out there, and you can kind of tell what they do by looking at them. Logistic regression. There you go. If you fit one layer to an image, you get a gradient. Doi. Basically, this thing can't fit to it because it's only got one layer. This is the picture I used to show how adding a second layer to your neural network makes it an arbitrary function approximator, whereas single layers really can't, because they can only do linear divisions. That second layer adds tremendous power to the neural network. Baseline. That's the average pixel value. Obviously not very great. And here's that's garbage. Okay.